You're listening to Revolution Radio, where it's 53 degrees, and I've got Joe Anunnaki on the phone. Hey, Joe, what would you like to hear?
We are observing your Earth.
I'm sorry, Joe, but we can't...
And we'd like to make...
sorry, Joe, but...
a contact with you.
Collision Course.
It is essential for our survival to use these powerful tools in the most humane and wise way. And the only way to guarantee that is not to shuffle the responsibility off to somebody else, but to make sure that every citizen understands science and technology to some extent.
Lighten up, Francis.
Revolution Radio! All right, thanks for listening while we took that short break here at Revolution Radio, freedomslips.com. And now we're going to get back to your host. Good evening, everyone. It's Francis for another episode of Collision Course right here on Revolution Radio, freedomslips.com. It's 8 p.m. in New York City. Welcome to everyone in the chat room. If you're listening to me right now, you can hear my voice, and you're here to listen to Collision Course. Join us over on freedomslips.com. Inside the chat room, I leave links and pictures and try to keep up with questions, and you can ask me questions to ask the guest, because we have a great guest tonight, Dr. J. Craig Wheeler, an expert on collapsing stars. So let's get on with the show right away, because he's going to be waiting for us. Clear skies, everyone. It's Francis, your host of Collision Course right here on freedomslips.com, Revolution Radio, every Sunday from 8 to 10 p.m. Eastern. You're going to join me right here, and I'm going to tell you a little bit about what's going on in our solar neighborhood. Not just that, though. You know, we're on a mission to uncover and discover the truth about our place in the universe. Come listen for the interviews like the one tonight with J. Craig Wheeler, doctor. Listen to me. Either way, we're going to know more so we can decide what is real and what is not in the space outside our atmosphere. And that's why you're here with me tonight on Collision Course. And guess what I'm going to go ahead and do? I'm just going to go ahead and bring in the guest, Dr. Wheeler, and let's just get on with the discussion about supernovas, because tonight's discussion is supernova, and we got 2 hours. First hour is going to be the discussion with Dr. Wheeler, and then we're going to talk about what we talked about and everything else that's going on. Basement 5, hello. Let's just say hello. Basement 5, hello from New Hampshire. Hello from Cyprus. Reggae Girl, hey. Greenheart 1, the jurist. Jersey Dolphins, is good to see you. Jersey Dolphins, as always. Pat Rabbit, Mr. Rowe, Omega Logos, Ginap, Francis in there, Corey, 1967, Mitchell, Megaloris, The Jurist, Popsicle Toe, Stardust Man, SJ, Wall E, Mace 139, and Comet, hello. Let's get on with the show. Adding Dr. Wheeler. Dun-dum. Dum-dum-dum-dum. I hope everyone is doing well. I shouldn't stop talking because I really don't like dead air. I hope everyone's doing wonderful this evening and is having had a very good weekend. Coming together on a Sunday is a great thing to do at the end of a Sunday between 8 and 10 p.m. Because we get to talk to wonderful guests like Dr. J. Craig Wheeler. Dr. Wheeler, are you on with me right now?
I'm on with you. Yes.
It's going to be an audio. I can see you, and that's fine. I don't know if you're going to be able to see me, though.
That's okay.
Okay. And I didn't hear an echo, so that's great. We're good to go. How are you, Dr. Wheeler? How are you?
I'm very well. Thank you very much. Looking forward to the conversation.
I'm very excited. I'm very excited because not only are you a wonderful scientist and doctor, astronomy, supernovas, but you're a writer. And writers
also true, yes.
And writers have great
ideas and thoughts that go outside of known science, and I'm going to have a wonderful discussion with you. But our discussion tonight for the listeners and you and me, because we really didn't have very much set up, is going to be about supernovas tonight, high energy events that happen in the universe. We're going to bring it together with Betelgeuse because we have a lot of interesting information from Betelgeuse, and then we're going to talk a little bit about your fiction and your stories, because Krone's experiment is very exciting to me and its idea. So, I pulled up an older paper from 2002, but rather than me really reading it, let me just ask you, can we just give an idea of what a supernova represents in the universe, as far as it is a catastrophic explosion that...
Well, yes. So they blow up, they get very bright, they forge new elements, sort of all the elements that we know that are heavier than carbon. Some carbon is made in stars that don't ultimately blow up. But all the heavier elements from oxygen on up, so many of the elements that we need to make life come out of supernovae. They make fascinating things like neutron stars and black holes sometimes. We can use them to measure the expansion of the universe and determine that it's full of dark energy. So they're a tool to explore the universe as well. They basically connect to everything. I do have a slogan on my webpage that says it's all one universe, and that's what I mean. It is all interconnected. But you can start with supernovae and connect to practically every other kind of astronomy there is, and life on this planet, for that matter.
Because in essence, everything that's in the universe, can be generated from that massive explosion of energy. Now, when we look at supernovas, and when you just said that statement about what they are, there's probably 3 or 4 questions that you can ask specifically. And I suppose the one that always comes to my head first, and I don't know why this is how can we measure the universe with the brightness of a supernova explosion? And this was the one question that I don't understand.
Sure. So it's a process that's called a standard candle. There's variations on it. But the idea is if you picture a light bulb, a 100-watt light bulb, so you know exactly what the power of the light bulb is. It's 100 watts. And then you carry it some distance away, it will look dimmer. And if you take it twice as far away, it will look 4 times as dim, because the light spreads out through the area, and the area goes like the distance squared, to be a little technical with the audience there. But you go 10 times as far away, it looks 100 times dimmer. So if you know it's a 100-watt light bulb, and you see how bright it looks to your eyeball, or for a supernova, how bright it looks down your telescope, you can tell how far away it is. You have to know intrinsically how bright the supernova is, and there are some issues about establishing that. But I'm more interested in how they blow up, frankly. But I have colleagues who have spent massive amounts of their career over the last 50 years, several generations, trying to figure out how do we determine what the intrinsic brightness, how many light bulbs does it take to make up a supernova, and then how dim does it look through a telescope, and thereby measure how far away that supernova is, and then do that hundreds and hundreds of times, ever more carefully, and find out that, for instance, the universe is accelerating, even though it's nominally under the grip of the gravity of the material in it, something that we call dark energy, that we don't know what it is, except that it's pushing. It's an anti-gravitational effect that is causing the universe to accelerate away. Everything moving not only just away from everything else, but moving faster and faster and faster away from everything else. A very dramatic discovery by my supernova colleagues about 20 years ago now.
Okay, so basically you have more knowledge about collapsing stars, and we can rather than the measurement of
some collapse, some blow up entirely. I have a token knowledge of all of it.
And I guess just before I leave that last part, because I asked the question, so I guess what the scientists may be attempting to do is find similar stars at different distances, and then they can say that supernova should be a certain brightness, And
Yeah,
that's how
exactly so. So there's a whole zoo of supernovae of different properties, but there's a kind that we call type 1A for technical reasons. I could talk about the history, but not terribly important. But they're quite homogeneous, not exactly homogeneous, but pretty homogeneous. They all seem to do basically the same thing. And so if you identify one, you say, aha, it's one of those, and we have figured out how bright those are. And so that's the favored tool for measuring the universe. There are other techniques with other ones, but that's the most straightforward. It is basically they are a candle. We know how bright they are. We know how dim it looks through the telescope. Bammo, we can figure out how far away it is.
Excellent. Well, let me curve around again, because the star with the most highlights of the day, it happens to be Betelgeuse. And I guess since Betelgeuse is in the news so much, I know my listeners and I had the discussion with Ed Guinan
that was a wonderful discussion. I listened to the whole thing.
I loved it. He was very good, and I really enjoyed it. And I try my best to research as best as I can. Sometimes I'm great on it, and sometimes I'm not so great. But with Betelgeuse and with this discussion about supernovas, and with what you said about really understanding maybe about collapsing stars, let's look at Betelgeuse. Betelgeuse is a supergiant, has a lot of dust around it. Can you take it from where I just stopped? If I were to say Betelgeuse is a large super red giant, I know that it has a lot of dust around it, and they're telling me there's a lot of this activity, dimming, maybe shrinking. Can you describe to me what may be going on in that star's life and in its neighborhood?
Let me take a step back just to tell you and your audience sort of how I got into this and thinking about Betelgeuse in various ways. And the recent dimming has certainly caught everybody's attention. But for a very long time, I taught a course for non-science majors, basically a popular audience here at the University of Texas. And it was on supernovae and neutron stars and black holes and all those interesting things. It was a wonderful course. I really enjoyed teaching it. And I added because it was a lecture course, so they have to stand up and listen to me lecturing for 50 minutes, 3 times a week, that I wanted them to get outside and look at the night sky. And so I invented a series of extra credit projects where you go out and look at a part of the sky. You might be able to see an object of interest, but at least you can know you're looking in the direction of the supernova that Tycho saw in 1572 or something like that. So I have them doing these outside projects. And an obvious one to do when I'm talking about stars that might blow up is to talk about red supergiants. And then the obvious thing to do there is to look at Betelgeuse, because you can walk outside at this time of year. It's just up in the evening. It's easy to see. Anybody of interest after your program, it's cloudy here in Austin tonight, but you ought to go and try and look. It's just Orion is up and dramatic and big, and you can see Betelgeuse so easily. So I would do this. I would have them look at Betelgeuse. And then in the lecture, I would say, we are so ignorant of what's going on inside that star that we don't know when it's going to blow up. It might be a long time from now, but we are sufficiently ignorant. It might blow up tonight. So I want you to go out and look at that star, and if you see it getting brighter, let me know, because that will be very exciting. And I've told this story now to thousands of students over quite a long time. And so that kind of set things up. And so I would tell that joke. We were very ignorant, go out and look at it for a very long time. And then I realized that was really a serious scientific issue. We really don't know when Betelgeuse is going to blow up. And we should try to do something to resolve that. So I set out about 10 years ago now, thinking on my own and working with some undergraduates here at the University of Texas. A couple of them still involved in it who are now graduate students at Berkeley, Jamie Sullivan and Serafina Nance. And we're still writing papers on Betelgeuse that stemmed from my having a slightly tongue-in-cheek statement about what Betelgeuse may do and when, to try to actually get some science out of it. And the idea would be there might be some, as the star ages and it makes heavier and heavier elements down inside the core, it will eventually make a core of iron, which will collapse down to make a neutron star. We can talk about some details of that. And that implosion will generate a huge energy that results in an explosion and blows the star up. And we're confident that's what will happen to Betelgeuse. The question is when. And so we looked at that, and the question arose as you get closer and closer to that critical iron core, could there be a commotion on the inside of the star that in some way would communicate itself to the outside, maybe subtly, but you might be able to see some precursor information that would tell you that the star is getting close to that explosion point. And so that's a real scientific issue. What would the clue be? How would Betelgeuse generate that clue? What would you have to look to see that clue? So that's what sort of got us going on this. And it's
Can I stop you for a second?
But that's the basic idea. It came out of teaching this popular course and turned into a scientific passion.
Since you brought the question, what would we look for? I have a question.
Sure, please.
Would things
and we can get back to the dimming. I'm sorry, I really wanted to tell that story that way because that is how I get into it.
No, because actually, I want to ask let me see if I can get both questions, because once the questions start, I don't know if they start walking over each other.
Okay.
I tell my listeners, and I'm an active astronomer with Outreach. Every month we do a star show, and next week we have our star show. So I tell people, go out and look in the sky. You can do it with your mind. You can do it physically. You said, tell me when Betelgeuse is getting bright. Do you think before if it were to go supernova, now that it's dimmed, would it go bright before it went supernova? Or are we just talking about the brightness of the supernova?
I think the honest answer to that is I don't know.
Okay.
There is, I have a colleague at Caltech who has written an interesting paper pursuing the same kind of idea that we were here. That is, could there be some commotion on the inside that would be communicated to the outside of Betelgeuse sometime before it blew up? Years, decades, days.
So,
and his theory is that there would be a commotion on the inside, and that would send a weak pressure wave, a shock wave out that would hit the outside and cause it to temporarily brighten, and then it might dim for a while, and then in the wake of that dimming, it might blow up. Right. About a year after the dimming. So running around the Twitterverse has been some issue of whether Betelgeuse might blow up not within days, but a year from now. I think there are counter-indicating signs, because he basically predicts that Betelgeuse would start expanding, and Ed Guinan's observations are that Betelgeuse is contracting. It's slightly gotten smaller during this dimming phase. And that's just the opposite of what my colleague at Caltech would predict. So I think his theory doesn't apply directly. I think we're going through some other, for Betelgeuse, natural dimming phenomenon. And that my guess is still, for better or worse, it's probably more like 100,000 years before Betelgeuse will blow.
Well, I have to ask.
So if you want to get into the technical details. But
I have to ask this. My favorite Nobel laureate, Dr. Charles Townes.
Yes.
Who spent the last 15 of his great, wonderful years measuring Betelgeuse. And I'm going to ask you the question because I want to, right? And so he measured in his discussions a 1% decrease in size of Betelgeuse from the 90s till near his death in 2003.
Yes.
And you think he trusted his measurements? And so if I'm asking this question is, are those measurements something that we can carry into these observations, these more present, or are we not looking at that at all? Is that information been?
That's a really good point. And I actually did my undergraduate research on lasers, not on Betelgeuse.
Yeah, lasers and masers. Yes.
I mean, I had just signed up to work with him when he won the Nobel Prize, so it was quite an exciting time for a junior college at the time. And I'm very much aware of those observations and thought about them as we were writing our first papers. It was a fairly slow contraction over like a decade And of course, he measured it over a decade ago. So I think it is not irrelevant, but I don't think it's directly relevant to this dramatic dimming we've seen since last December, just over a couple of months. I think that's some different phenomenon, which I think Charlie would be fascinated to see and think about.
Well,
I don't think it's directly related to what he measured.
Let me move in with the
controversial. There were some people with some contradictory information.
Yeah, and Ed was in the middle of the road also, because there was a report later that there was some, discussion about accuracy or not, interferometer. I'm not quite sure, but I do want to add that in because, again, it was 15 years worth of data. It was a very brilliant mind. So I know myself, I don't like to waste my time, and I really can't imagine that he would waste it any of his time either. So I never like to I'd like to add that in there because for my listeners, they're trying to get every bit of information. They don't have time to dive into this research or even know maybe about Dr. Towns, but it is relevant because he was doing research before this more current. Now, I have a question.
Sure, please.
The sloughing of surface material, and because the environment around Betelgeuse is very dusty environment, that makes it a part of the reason why it's hard to measure its size or actually see its surface because the amount of dust and sloughing.
It's a little fuzzy. Yep.
It's so fuzzy. And then actually to get to the star to measure it, you have to be coming at it with certain wavelengths, right, to make it easier to see through that dust.
Yeah, you see different in optical light that we see with our eyeballs than you would with infrared light, longer wavelength light that would penetrate that dust more effectively.
Is this dust measurable observationally? I mean, we're looking at the star, right?
Yes. Yes, I understand the question.
and so we actually have a moving star. The star is moving at 32,000 kilometers a second. It has a bow shock. It has all this environment going on. It is a very dynamic place already.
So I think the dynamics are fascinating, and they bring their own puzzles to Betelgeuse. We could talk about that, but the dust is being formed by the star. The star is blowing a so-called wind. It ejects material off its surface. Some of that material come off the surface. The heavier elements, so-called refractory elements, will coalesce into dust, make tiny grains of grit, and so the star is producing its own dust, and that does. If you're interested in how dust is formed around a star, that's a topic unto itself that some Betelgeuse experts are studying.
But is it a signal? It doesn't come back as a signifier of any rapid development. I mean, I guess the biggest observational point is the brightness. Is that really what's is that what everybody's keying in on? There's nothing else.
It's conceivable that the rate at which mass is being lost could signify something, but it's a rather indirect indicator. So what we were pursuing is a question of whether if the insides of the star are turbulent and messy in some way, they might send waves out, and those waves could impact on the outer surface, and you could see a very faint modulation of the star getting brighter and dimmer on rather short time scales, months, something like that. But as we worked out the models, it turned out that Betelgeuse's great big sloppy red giant envelope would tend to eat up those waves, and they wouldn't get to the surface. So that was the result of the second paper we wrote, was that that's going to be hard to do. The mass loss itself, or the dust formation, is an inexact measure that doesn't tell you. It's a buffer. It kind of buffers the information you would like to see, so it's hard to see those details. So then just to segue from that, Betelgeuse is a variable star. It gets brighter and dimmer as red giants are wont to do, and we've been watching that for a very long time. And then all of a sudden, for those of us paying attention now, and I must admit I didn't pay attention right away. I was a few days late, but it started this dramatic declining by a factor of 2 or something like that. I took my wife out to our upper deck a couple nights ago when it was clear for the first time in a while, And she looked at it and said, hey, that star is dim. She hadn't looked at Betelgeuse in a very long time, but she had enough memory to realize that star has certainly changed. So to see it change on a human timescale, a couple of months, and to change in a gross way that you could just casually go outside and see it, quite remarkable event. But one of the pictures I sent you, and we don't have that immediately available, so if I could just describe it, was the 120-year-long record of the Amateur Variable Star Society. So they have a lot of people going out and looking at a lot of things, including Betelgeuse, and keeping records of them. And you can see Betelgeuse getting brighter and dimmer on timescales of about a year, which are fairly well known and sort of understood. And then my impression in that picture was that Betelgeuse got about as dim as it is now back in 1940. And then it did it again in about 1980. And here we are 40 years later, and it's doing it again. So I think we're seeing some kind of natural, amplified, oscillatory behavior that has brought this particular dimming. It very much to be understood, but not a signifier that it's about to blow up. And then the latest thing is that just in the last couple of days, people have been tracking it very carefully. It looks like it has bottomed out and starting to get brighter again. So if your friends listening here want to keep track of it over the next few weeks, my bet is it's going to get brighter and get back to what we consider sort of normal over the time scale of about a month, would be my guess.
Well, which is great. And listeners, I'll tell you what, now that what Dr. Wheeler just said is actually one of the first times I heard anybody say it, because all the information so far about Betelgeuse is, watch. He just laid out a full...
You should actually watch. Absolutely.
We should, but I mean, we also should understand that maybe we're looking at a 40-year cycle. We know that we should know that our sun is working on an 11-year cycle, give or take. But Dr. Wheeler just pointed out that 40 years, are we at 40 years? And maybe we need to look into it farther. But even if it is 40 years, isn't it an interesting time to have a star acting the way it is? And as observers, it's going to give us this experience of observing it, which will realign our point of view, which is always good when we're looking into the universe, because if there's anything citizen scientists can do is look into the universe and get answers like that. We can look at Betelgeuse and say, that is changing. Let's go on the news and see what the scientists say about it. Scientists are saying maybe it will, maybe it won't. We'll just keep listening. And then you come to a collision course, and we get to listen to Dr. Wheeler, and Dr. Wheeler gets to put it in perspective. And maybe now we're at a bottoming of the curve. And maybe Betelgeuse, and I say it multiple times because I'm never quite sure which is right.
I've adopted Betelgeuse, but frankly, I don't know exactly how you're supposed to pronounce it.
And so... if we're at the basin of the curve and we're going to maybe lead upwards, much like our own sun, and I have a question for the doctor about our own sun as well. Maybe what we have to do now is carry this discussion of Betelgeuse into our observations into the future, go out when it's clear, look up. Like the doctor said, his wife, I mean, I can see it. I know anybody who goes out and looks at Betelgeuse, you can say, I remember looking at Betelgeuse and it was one of the brightest stars in the sky. It used to be the 11th. It used to be the 11th brightest star, I believe, in the sky. Now we're down to like 26th, so we're in the 20s. So that kind of major dimming of light we can all see. So even if there's no grand event, there is an interesting event going on. So
no question, and question. Deep scientific questions to be resolved. But if there is this 40-year cycle, what is that? That may just be my fantasy. I've not heard anybody else tell about it. But yeah, there's things scientifically we really need to understand of what's going on in this dimming.
Well, this is one thing we know on this show is we don't stop from thinking. Anything is possible.
Yeah, keep thinking. I seem to have lost the sound. Are we there?
Yes. Are you not here with me?
No, I'm back. Yeah, I may have clicked on something.
What I love about the universe so much is that there is still so much to learn, and we don't have to have the answers. We just got to keep on searching. I have a question. Excuse me. Our sun. I just want to ask the question because you have experience with supernovas and stars. Do you have any experience with stars like our sun and the end of its life? And could you give our listeners an insight into the ending times of our own sun, though they may already know and have heard that story?
Sure. I think we know that story pretty well. We see it playing out in other stars as we look out through lots and lots of stars in our galaxy and elsewhere. We have very sophisticated computer models that say what would happen to our star. You got to be a little careful about literally taking theoretical models, but it all comes to the same picture. I think we know quite well what's going on, that the sun's 4.7 billion years old. It is burning in a thermonuclear sense. It is converting hydrogen into helium in the center. That phase has another roughly 5 billion years to go until the hydrogen is all consumed in the center. It won't be consumed throughout the whole star. The outer parts of the star will still be made of hydrogen, but it'll burn out on the inside. And then that will trigger changes. The inside will shrink down to be roughly the size of a planet, about the size of the Earth. It will basically have formed what we call a white dwarf star. But to become a white dwarf, the center parts contract down and become quite small, and the outer parts will expand to become a red giant. Not a red supergiant like Betelgeuse, but a solar mass, one solar mass red giant, of which we see many, many, many out there in the galaxy. And so you form this extended envelope. The outer parts of the sun will expand out, will envelop Mercury, will envelop Venus, might envelop the Earth. The question of whether the Earth might drift outward a little bit and stay ahead of this thing. But life on Earth will go away. Certainly at that point, it'll get very hot as the star expands out. And then that outer part that is expanded out will itself be puffed off by forces of radiation pressure of the light coming out of it, and blown off into space, become what's called a planetary nebula, which has nothing to do with planets at all. That's a historical thing we're stuck with. But that outer parts of the sun will drift off into space, leave this object behind, which is about the size of the Earth, but with the mass of the sun, half the mass of the sun, and then become a so-called white dwarf. And then it will stay that way forever. That it will just cool off and cool off and cool off until the universe evaporates or something. But basically, that's what will happen. So it will be a disruptive
planetary nebula,
but not an explosive ending. It will not make a supernova. The same kind of star, though, a white dwarf, if it had a companion star, a binary star, that could add mass to it, is the kind of thing that blows up and makes this very standard supernovae that we use to measure the universe, the so-called Type 1a supernova. Those are exploding white dwarfs, and the white dwarfs come from stars like the sun, but in a double star system.
Okay, so the sun by itself isn't a Type 1. You need the sun plus a binary.
You would need another star.
For the type.
And we, there may be a Planet 9 out there or something, no companion that will help this sun. Some will not. It will be.
Well, Doctor, when you bring up Planet 9, you're getting really close into some really long discussions about binary systems in our sun. But I want to go. Before we go there,
I'll squeeze out of it. Having raised the point, I'll squeeze out of Planet 9.
When we, it's interesting research, though. I mean, just in itself, and I've talked to other people about it. But I skipped over it. Let's look at Betelgeuse and what happens if, because it's going to be a different remnant, right? It won't be a planetary nebula like our sun's remnant after it goes supernova.
Quite different. So
let's talk about Betelgeuse then.
There's some controversy about what it will look like, but I'm modestly confident that it will blow up and make a certain pattern of light, which it'll be about as bright as the moon, but not as big as the moon. It'll be a tiny point of light in the sky, about as bright as the moon, and that'll last for about 3 months, and it will fade away. That's what we'll see on the outside. On the inside, you will have this making heavier and heavier elements. The reason I think it's still 100,000 years before Betelgeuse will explode is just a time scale argument, that the longest time a star lives is when it's burning hydrogen into helium. The second longest time it lives is when it's burning helium into heavier elements like carbon and oxygen. And then it gets faster and faster and faster. And you just ask yourself, what is the probability that it's in a given burning phase? And the answer is it's in the longest phase, just probability-wise. It's no longer in the hydrogen burning phase because we know it's a red supergiant. But the odds are about 100,000 to 1 that it is still burning helium into heavier elements, and it hasn't gotten into that final state. So that's my guess. It's just strictly the probability is highly weighted that it is still burning helium, and that takes 100,000 years. But then eventually it will burn out the helium and the carbon and the oxygen and silicon, and it'll make this iron core. The iron core will collapse down to make a neutron star, which I said that triggers the explosion. You blow off the outer parts of the star, and you leave that neutron star behind. So that's what's going to happen to Betelgeuse. It'll be as bright as the moon for about 3 months. It will fade away, and it will leave behind a neutron star. That neutron star might be rotating and magnetic and be a so-called radial pulsar, of which we see many, many. We do not have the ability to predict what particular star will make what rotation rate of its neutron star and what strength of magnetic field. So we can't predict that in detail. Another interesting thing about Betelgeuse is there is some controversy about which stars will explode and leave behind neutron stars and which may explode and leave behind black holes. And that controversy sits right about at the uncertain mass of Betelgeuse. So we don't really, if I had to bet, I would bet it will make a neutron star. But there is a finite possibility that it will leave behind a black hole, that Betelgeuse sits right on that controversial mass range where we really don't know what a star will do. Makes it all the more
and that's and that, and the news reporting has basically covered a lot of those things. You can, if you read 5 or 6 or 7 or 10 or 20 articles, you'll be able to hear this. You'll be able to hear the different results of what it could be, neutron star. Not. But let me, before I get there, you said a point, because this is something that I need to learn, and the listeners need to know that I need to learn that. In my mind, I painted a picture in my own mind when Betelgeuse blows up, the sky is going to be like painted with all this light, and the doctor just told me the truth. And he said, well, Betelgeuse, when it explodes, it'll be a point of light that's about as bright as the moon, not something that's
with a big telescope or the right sort of way of doing it. You might tease out how bright it really looks, but not to a human eyeball. It's going to look like any other star that is a point, but really, really bright.
And what do you think as far as, small and big stars? Would we go out there and say, why, that's a big star, or that's just a normal kind of?
We had to do a lot of very careful astronomical work over the years to tell. Some of those lights out there, you can actually kind of make out a size a little bit, but they turn out to be planets in our solar system. And all the things that are stars other than the sun, if you look at them with your eyeball, they look like a point.
Or a point of light.
Because they're so far. Right.
But did I read correctly that Betelgeuse is actually the one star where it's not a point of light?
It is near enough that with amazingly sophisticated astronomical techniques, you can actually take a photograph of it to see how big it is. Not with your eyeball.
Yeah,
but with very fancy, sophisticated techniques. A recent picture that just came out a few days ago, and I think you're putting on your loop.
Yeah, I think
it shows a kind of bright spot in the upper left and kind of dark everywhere else. That you don't just go out with your Kodak and take a picture of that. It's a hugely sophisticated process to tease that.
That was the large. Was that the LSST, the large synoptic? No.
No, it was a very large telescope in Chile run by the Europeans.
The VLT in Chile.
Yeah.
Who took that? Yeah, I've basically come down to describing Betelgeuse as almost a kernel of corn when I'm trying to describe it, because when you look at those pictures, you can almost see the three-dimensional, just non-sphericalness kind of sort of to it, but I'm not really quite sure too. But it's really interesting. It's an interesting topic.
It's a fascinating picture and just an admirable piece of science. Really terrific.
And so I've been really enjoying talking about it, and I'm going to continue talking about it because I'm going to find papers and research and new research, and I'm going to be recommended. Like Ed, you can blame us talking on Ed Guinan, because he said right in that discussion, if you wanted to talk to someone who really knows about collapsing stars and supernova, Dr. Craig Wheeler is the guy, and that sent me right over to you. And you were so nice to join me on tonight's discussion, so I do want to take a moment and thank you for joining me and for informing myself and the listeners about things, because I'm learning, and I'm going to learn for every week that I put on a show. I'm going to learn something new. I want to spend a little time, because we have about 15, 16 minutes left.
Okay.
And I've left the links of your other writings and the other things that you asked me to in my little blurbs, and I'll do it here in the chat room. I want to talk about this experiment, the Crone. Is that how you pronounce it? Crone experiment?
Yeah. Mm-hmm.
And now for the listeners, he's a writer, and I find writers, because I like to write. I haven't actually published a book. I'm sorry, but I do have lots of stories.
Publishing's hard. I've got a couple. I've got others I want to publish, and it's hard to know how to get them out. So.
But what's great about it, when you talk about it with a scientist and someone who's of science, is that that you can trust that he isn't necessarily in a science envelope, that he can take ideas and thoughts and write stories and create scenarios that could be potentially the truth. We just don't know it yet. And the Crone experiment has to do with particle accelerating and smashing together at CERN. Correct? And what happened?
I had the idea and wrote the book long before the issue of whether CERN was relevant came along. But I got lots of emails from people who had read the book, said, "Hey, do you hear what's going on with CERN?" And I said, "Boy, if I had a nickel for each one of those emails, I'd probably have 25 cents by now."
Well, let's talk about how close your book can be to truth. Tell me about your book and what the story is, and then I'll link it.
Right, it's a little awkward because it's kind of a contemporary science thriller mystery. So there's kind of something to be figured out as you read it. So if you ask me what it's about, it's like telling you, well, it's a book about the butler did it. But, I won't tease your listeners, though. No, the premise is that someone has managed to make a small man-made black hole. And so the mystery is reading about what's happening to the Earth and what signals there are and the people who figure out that's what's going on. That's what the story is about. And the basic premise is pretty outlandish. That is, so the question was at CERN, if you smash particles together, might you make a small black hole? That really was a concern when CERN first came on the air. There was a guy in Hawaii that was trying to sue them to stop them from building the device. It was always a silly argument because we have cosmic rays hitting the Earth with more energy than CERN can provide all the time and hadn't made any black holes. So I don't think it's a realistic thing. So the idea that it could be done man-made, and I tried to put enough arguments together to make it sound kind of plausible. But that's the basic novelistic license to say, suppose there were a black hole made and released to the surface of the Earth, and then it would plummet through the Earth, and it would basically orbit inside the Earth, up and down as the Earth rotated around. And that part of it I tried to think through fairly realistically. That is, how long would it take for the black hole to go down and come back again? How far would the Earth rotate during one of those cycles? Where would it come up? What would it do? I tried to make that as realistic as I could within the construct of a novel. Having
in that
outrageous premise.
In that description, like usual, and it's another saying of mine, truth is stranger than fiction, because you just said that there could be natural events, and this is something you're an expert with, high energy events. So tell us about, let's talk about, Earth is, unbeknownst to most people like myself, being subjected to high energy events occasionally. Are they frequent? Are they, and when we're talking about, so let's say when you said that, I'm thinking, what is there, two high energy events coming in opposite directions occurring at the point of Earth?
You don't have to come in opposite directions. If you have one thing standing still, like a particle on the Earth, and you bring in another thing with a very high energy, they will collide with high energy.
Oh, okay, yeah.
Think of a bullet hitting a target. The target, you need to be going toward the bullet. Thank you very much.
Just had to have a perfect hit, that's all. So, let me ask you then, because you've been researching these for a number of years. You've known and been involved in this. What type of numbers are we talking about, and what type of energies are we talking about? And because these are types of events that there's no reporting on. You know, we'll get reports about when an asteroid's going to come real close because that's something that easily tracked. We can watch solar sunspots and solar flares and CMEs leaving the surface of the sun pretty easily as citizen scientists and people like myself. I guess it's the same place, right? They have the gauges that register gamma rays and X-rays that are hitting Earth, that are accessible almost similarly.
Yeah, you can measure. So a lot of that material, particles, incident, radiation incident is stopped by the Earth's atmosphere, which is good for us. It would be uncomfortable to be exposed to it. But there are scientists who build equipment to measure those things, and we see them all the time. So there's this constant shower of cosmic rays, which are particles of matter, protons and electrons and other particles. And then there's also a shower of high energy photons of radiation. And we're constantly bathed in those. And there are experiments that are built distinctly to detect that cosmic rays and high energy radiation of various kinds.
And neutrinos. Oh, here's a question. I remember this question.
I've got a neutrino story too that you may not want to get into, but go ahead.
We got 10 minutes left, and we're going to have a lot to talk about, but we're going to go right to the end. The actual notifications of Betelgeuse exploding, will they be neutrinos first, gravitational wave second, then the explosion?
Yes, I think that's because the neutrinos are already going to start to happen as the iron core collapses and all the protons are turned into neutrons in the process of forming the neutron star. So the most intense neutrinos will come as the neutron star is forming and hitting bottom, but they will start before that. So that's probably the thing that will come first. Then as the neutron star forms is when it is most irregular and will make the gravitational waves. So the gravitational waves will be almost simultaneously, but maybe slightly behind the neutrinos. And then that will create, the whole process create a shock wave that has to run out through the star at sort of the speed of sound, not the speed of light, out through the star, and that's slower. And so it will take a day or more before the shock wave hits the outside, and then we will start to see this bright point of light. So
imagine the science.
Yeah.
Imagine how much science could be done if that event actually happened and you're able to, rather than, because I read somewhere that the largest neutrino collection was like 25 neutrinos. And then if something like this were to go off, I read it would be like 25,000 neutrino hits.
Yeah, I saw that number. Did I see it from you somewhere? I saw that number and I tried to estimate it myself. And it seems to me to be a lot more than 25,000, but
sensor reading by how many the sensors
the joke about myself, though, in my Cosmic Catastrophes book, I told the story of Betelgeuse a little bit. I estimated the amount of neutrinos. I estimated the amount of irradiation of the human body by the neutrinos. And I said it's about 1,000 times less than the killer dose of radiation. And I gave a talk at Texas Tech a couple of years ago, and a guy emailed me afterwards and said, I think you made a mistake by a factor of 10 billion. You should check that again. And he had a very straightforward way of scaling from supernovae to everything. But I sat down before I gave this talk. I wanted to know what the numbers were. And he was right. I got the dimensions wrong. I scaled something wrong. It turns out that we will get irradiation from the neutrinos from Betelgeuse, but it'll be equivalent to like 1/1,000,000th smaller than a dental X-ray. So we're not in any danger from the neutrinos from Betelgeuse. If anybody out there about it, because of my error, it's not a problem.
Well, as Well, at least I do. I give myself the opportunity to, have this envelope that I work within. I cannot say for sure sometimes, and I don't want people to take my word for sure, because I may have to go back and learn. I may have to go back and re-edit. I may have to go back, sometimes even retract. Sometimes we have to go back and retract what we say because you find out that the truth lies somewhere else, and that's just the way it has to be. But don't be too afraid. Don't stop yourself from going out and finding the truth, because the truth is out there. That's the best part, and that's why we come to Collision Course every week, and we talk about outer space, because we like to talk about truthful things in an honest way. Because, Dr. Wheeler, you can go out there on the airwaves these days, and they'll talk lies about outer space all the time, and it's just, to me, it's never been my point, and it just isn't right. So we like to talk to scientists.
You're doing an honest job, Francis. It's much appreciated.
And I'll tell you, like I said, I do the outreach. We sent a telescope over to Cameroon, Africa. I'm mentoring a teacher in Africa. So, and what I've been rewarded with is receptions like what you gave me to my email. Yes, I'll be happy to come on. Yes, I will. And I've always told my listeners, and they know this isn't the first time I said that, science and scientists and people that have the knowledge that we ask to know about, they'll come on the show. They'll talk to us. They talk about what they like to talk about and the things they know the most about. And with Dr. Wheeler, he knows the most about collapsing stars. Now, Dr. Wheeler, I wish I knew more. Okay. To be honest with you, I wish I knew more and I could be more in depth and more knowledgeable when I asked your questions. So I hope that I didn't miss, for my listeners' sake, anything that's really important. What we can take away, listeners, is this. We can use supernovas of a type 1A to potentially measure the distance of the universe from this side.
Not just potentially, we've done it.
We've done it. And Dr. Wheeler has told us that it's accelerating, that the acceleration is according to, because we don't know enough about dark energy and dark matter. Do you think that might be what's stopping us from understanding what's really going on with the shape and growth of our universe, Dr. Wheeler? The lack of knowledge about dark energy and matter affecting our understanding of the shape and size of our universe?
In the sense that is the problem. How is it expanding and how is it accelerating and what are the forces that do it? Those are all bound in together. So you got an observational fact that is accelerating. You're seeking the understanding of why that's true. Those are all bound together. It's all trying to understand is what the whole quest is about.
And you believe there is dark energy and dark matter in the universe?
Dark energy.
It's hard, I know, but I have to ask.
Cover a phenomenon that we have measured. We have measured the fact that there's anomalous amounts of gravity in galaxies, and we ascribe that to dark matter, which gravitates. And we have seen that the universe is accelerating. That's a tricky concept. The idea the whole universe is accelerating. The universe is accelerating, and dark energy is just our filler word for what is that process that's causing it to accelerate, and we don't know the answer to that yet.
Yeah, an effect that we cannot see, an effect that we can't see necessarily, and that's fine.
Neither are producing light. That's certainly true. That's why they're called dark. There's no light associated. I had one more question, and it's going to slip my mind. We're at 8:53 p.m. in New York City. We just have a couple of more minutes with our guest this evening, Dr. J. Craig Wheeler. I'm going to, again, of course, we have this show recorded, so I'll be able to leave you a link after the show. Doctor, you can listen to the interview. It was wonderful to have you on. I wish I could get this last question out of my head. I don't know if I'm going to be able to. I found it. Great.
It actually comes out of the chat room, and I don't know if you're going to have any knowledge about fast radio bursts.
A little. I've tried to follow it a bit. I have a colleague works just around the corner of me in the hallway who has been devoting his life to them for the last 2 or 3 years. Fascinating topic. Probably related to neutron stars in some way. modulation of the magnetic field making that radiation. This recent discovery, there's one that is somehow doing its burst every 16 days. I think that's brand new. I don't know what the smart people are actually saying about that. It may have something to do with a binary system. It's hard to see that it's too slow to be a rotation period. So I can think of some things it's probably not. But another just absolutely fascinating topic that's, I think, probably related to neutron stars, but even that's not universally accepted yet. There are people arguing about it. So if your listeners and yourself want to follow another exciting topic, then trying to see what's going on with fast radio bursts is a great one.
Oh, and we're going to. You can count on it. Now, you were about to drop a name. You think that gentleman that you work near that's been doing research on radio bursts for a long time, his name is?
Sure. Just the way Ed did, I could get somebody in trouble. Yes, his name is Professor Pawan Kumar. Pawankumar. He's here in the Astronomy Department at the University of Texas at Austin with me. And eating, breathing, drinking, sleeping, fast radio bursts for about 3 years now.
I love it. I love how that works. It's serendipity. It is the universe telling us where to go and how to do it. And that's how it happened when I got information for you to speak with you. And now I have information to speak with Mr. Dr. Pawan Kumar about
Pawan.
A.M. Pawan. I didn't finish the N. It was the N that looked like an R. So, Dr. Wheeler, we are coming to the end. Thank you so much for joining me and the listeners. If something big happens in the supernova realm of science, I'm going to call you back because I want to know what your opinion is and your point of view, and my listeners do too. I thank you so much for joining me, and until that time happens, I wish you the very best for you and yours.
Thank you for the invitation. I thoroughly enjoyed it. You have great questions. Good program. Really enjoyed it.
Thank you, sir. Thank you so much, and good night.
Good night.